cataracts or no, they're not.
Just
These things are actually,
how
there's some side effects, like the bark, you see the leaves.
Oh, yeah, okay.
All right, it's 2 o'clock, so let's go ahead and get started. Just a couple of announcements and general things before we get into the science topic for today. One, the barbecue today at 4. So hopefully you can all come. So to kind of put the class in, to put this topic and the rest of the class in context and outlook till next week. So far, you guys, we have been looking at, in addition to doing some Python coding, we have been looking at how to compute optimize the ground excited state geometry for molecules using the Gaussian program, but generically any electronic structure program. So this effectively, or well, in DFT it's not solving, but effectively you can think of it as solving the Schrodinger equation, computing the forces on the atoms and finding a position where those are 0. So far the geometries that you've computed are ground state geometries in the gas phase. So you can think of this would be the geometry the molecule would take in the gas phase if it doesn't see anything else, right? We will continue with that gas phase kind of idea today, but then starting next week we'll start to think about what happens when we have molecules that interact with each other and not just one or two, but multiple. And getting away from being able to solve the Schrodinger equation or basically fully utilize quantum mechanics to solve our problem. That will be what we move to next week. Today, the topic is excited electronic states of molecules. And so another thing that I've mentioned today, that you've done in the past, is use strictly the ground state surface to compute the optimized geometry. Today, we will think about what happens if we have a molecule, and why do we care about a molecule in an excited electronic state? And if we care about it, how do we compute properties of it? I will preface this with, we are not going to do any geometry optimizations on excited state surfaces. We are rather only going to look at vertical excitation. So what are the excited state energies, and what do the orbitals and optimized wave functions effectively look like given optimized ground state geometry of a molecule? Okay? So before we get into molecules, we're going to start with atoms and think about what an excited electronic state really means. Some of it, for those of you who have quantum mechanics, this should be a review. For those of you who have not, it is going to be an extremely cursory treatment of excited electronic states. Okay, so we think about the hydrogen atom, and we think of its electronic configuration, and it can be written, for example, as 1s1. Who has not seen this kind of notation before? Okay, great. So this just means that we have a single electron in the 1s orbital of our hydrogen atom. Now, as we were just talking about the history of this to some degree, at some time around the turn of the 19th to 20th century, the hydrogen atom spectrum was measured, and something like this on the top right of this screen was measured. And we can see that you have these quantized energy levels, or absorption bands, and they're named a variety of different things, but what they stem from is, in this case, it's an emission. These are denoted as emission bands, but you can think of the reverse being the absorption process. That the hydrogen atom, in its ground state 1s1, will absorb certain frequencies of light that are dictated by the gaps in energy between these electronic states of the atom. And the first one you might think of, and in the hydrogen atom, I should say, the n quantum number is the most important. So n equals 1, meaning we have the 1s. We only have a 1s orbital, and the n equals 1 quantum number, and you go to n equals 2, you will have the 2s and also the 2p, which are degenerate in the hydrogen atom. And you can see absorption bands between these different quantum numbers. So the first one is from n equals 1 to n equals 2. We are exciting the 1s electron into the 2s or 2p orbitals. And then so on and so forth. And you can excite into 3 and 4 and so on. And anything stemming from the n equals 1 is called the Lyman series, and there's other series that start from different initial states of the hydrogen atom, which we don't really care about so much for this. But what we want to do today is kind of try to understand how to compute these energy gaps and what the character of these excited states are. In the hydrogen atom, it's relatively easy to understand, but we're going to think about more complicated systems, start with helium in a second, and then move on to molecules. Okay, so these are pictures of hydrogen atom orbitals, 1s, 2s, p, and then d type orbitals, and they get more complicated from there. So why do we care about excited states? Color, dyes, those are all coming from electronic excited states. If your dye molecules did not absorb in the visible, they wouldn't have a color. Okay. You also have absorption of visible light, and UV light potentially in biology, in plants to absorb energy and make ATP, essentially. And then you also have energy materials, for example, solar panels absorbing light, exciting an electron potentially, and utilizing that energy in a variety of ways. So excited electronic states are important to understand the energy gaps that are there. But typically we think of this as a molecule in its ground state getting excited. And while that is and basically just computing that what we call vertical excitation energy. Now, if the excited state is long-lived, you might need to compute the excited state geometry, but we're going to ignore that for today. Okay, so in the hydrogen atom, we like to denote these sort of electronic energy levels in this way, where we have our ground state electron configuration, where we have a single electron in the 1s orbital. We shine it with some light, and then if the light has the appropriate energy to excite to the n equals 2 state, we will move that electron into an n equals 2 orbital. 2s. So one thing to note is in spectroscopy there are selection rules. The selection rules for this are called the port rule. Yeah, it's a singular thing here. But what it actually tells you is using light, you can't actually excite the hydrogen atom from the 1s to the 2s directly due to them having the same symmetry. So hydrogen has a center of inversion, and so you can't excite one thing from a 1s to a 2s orbital. So actually, you'd go to the p orbitals here. That's a limitation of spectroscopy, but not a limitation of quantum. I mean, you can show that from quantum mechanics by using the appropriate operator. But in the case of just solving for a wave function, we can solve for the 2s1 wave function, no problem. But that's something to keep in mind, that there are certain excitations that are forbidden spectroscopically. And so we'll not be seeing, for example, in the hydrogen atom spectrum, you would not anticipate seeing the 1s to 2s transition. Okay, so hydrogen's relatively simple. Let's think about helium. Helium, we have 2 electrons instead of 1. Ground state of helium is doubly occupied 1s orbital. And then if we maintain this sort of picture of the higher orbitals, we don't have splitting T's and S's. We excite one of the 1s electrons into an n equals 2 state. But this picture has some issues with it. Does anyone have any clue what is wrong, potentially wrong with the right-hand side here? Yeah. Well, okay, so it could be facing up, right? What would be the difference there?
I just remember when you started filling shells for Gen Chem, you started.
Okay, good. You do. Why? Do you remember why?
It's because the way that they're, sorry, this was not last semester, this was
Sure.
before. It's the way that how the shells, how, I don't know.
It's called
why.
Hund's rule or something like that.
Yeah, I was going to say there's a rule to it.
Mhm.
But
Yeah. So it could be facing up, but and it should be facing up if you actually want the lowest energy state. That's what Hund's rule tells you. So you could have one that's facing up, but you could also have one that's facing that is sort of like this. But the issue is the issue is what Tony talked about, the anti-symmetric part of the wave function. Okay, that the wave function must be anti-symmetric with the swapping of the electrons. So you can. This is denoting a singlet state, and what you're talking about is a triplet state. So the spin's going like this: 2s plus 1 is 3. So s is 1. 2 times 1 plus 1 is 3. In the case where they counteract each other, 2 times 0 plus 1 is 1. So we have a singlet state. So we will have both triplet and singlet states of helium in the sort of 1s 2s orbital configuration. So let's go through a little bit of that derivation. So I'm going to denote the atomic orbitals by 1s and 2s. And I have my electron 1 in the 1s orbital and my electron 2 in the 2s orbital. That's what I'm denoting here, which I will also write in the form on the right-hand side, which is just our electron configuration, essentially. But you can also have electron 1 in the 2s orbital and electron 2 in the 1s orbital, right? And that would be a very similar configuration. And from what Tony was telling you, these should be interchangeable, essentially, or you should have they should be anti-symmetric with respect to this. So essentially what we do is create this sort of superposition wave function, the 1s, 2s plus 2s, 1s, and you also have the negative superposition, which I call A. So we have these two superpositions. And essentially then what you have is you have a state psi s, which is the superposition of these two, and then psi a, which is just the subtraction of these two. Now, we also have to account for spin. So we have, those are what are called the spatial components of our wave function. We have spin configuration. So I should go back. Notice I have taken out the direction on my arrows. There's no arrow here, so this is just saying there is an electron here and there is an electron here, but I haven't denoted a spin on it yet. And we have these two, the plus and the minus superposition of the 1s, 2s spatial configuration. Now, if we think about throwing a spin onto those arrows, we can think of doing that in 4 different ways of those spatial configurations. One is to put them both up. The other is to put them both down. so denoted by alpha, alpha, and beta, beta, respectively. It doesn't really matter what alpha and beta is. And then you have alpha, beta plus beta, alpha, and alpha, beta minus beta, alpha. The top spin part of the wave function denotes a triplet, and the bottom denotes a singlet. And so that leads to the following two wave functions for our n equals 2 excited states. So the excited state that we might have denoted as 1s, 2s generically actually has the possibility to be both singlet and triplet, and has the following two wave functions, two complete wave functions with the spatial and spin components to them. And we can see that the triplet wave function here is triply degenerate. The singlet only has a single singlet. Okay, so to sort of kind of conclude this thing, we're going to go look at some orbits and orbitals and actually do some Gaussian calculations now on helium, then we'll move on to molecules. So even when we go from hydrogen to helium, things get a little bit complicated because we have this additional electron. And so even if we just want to go from the 1s doubly occupied ground state to the 1s, 2s, each singly occupied state, we now have a relatively complicated set of states. And we need to figure out ways of computing these. The methods that we can use, so methods that can be employed in Gaussian, for example, to try to get at these other determinants of our system, are configuration interaction and its variance, which we may or may not talk about, CAS-SCF, which could be argued as a variant configuration interaction, coupled cluster, and then time-dependent formalisms like TD-DFT, which we will not talk about today. So let's instead of belaboring the theory on this, let's actually go do some calculations and look at some orbitals and see how these things are computed. Okay. So if I'm probably going to do this locally, but you can follow along by either transferring files to your local directory from the cluster or whatever, or you can run on the cluster and follow along later. But you should, under your Luster file system, have a day4 directory which contains a variety of folders. Let's see, where am I? Yeah, so it should contain some subfolders like this. I probably should have deleted some. You actually don't need both benzene, mu, and benzene, but that's helpful. Okay. Here we're going to go look at the helium atom. So if you go into the helium atom directory, you should have a whole bunch of files. We're going to start with heliumatom.gn, just to look at, this was my initial run of this, and what I have here is very simple input file for computing the ground state energy of helium atom using the Hartree-Fock level of theory, the 6-311++ G star basis set. And the rest of it you don't need to worry about. By the way, we're denoting that this is a singlet by putting this 1 here. Okay? So this is the ground state that I want to start with. So we have the doubly occupied 1s orbital. So it should be a singlet. Now, we can just look at the log file to, this job has already been run. So we can look at the log file and see what happened. Mine went down to the bottom, but yours should start at the top. It should look something like this. And we can scroll through a bunch of stuff until we get to something interesting. Here it's doing some SCF cycles. And when we get to population analysis using SCF density, that's what I want to look at now. Okay, so I'm going to focus on this. It says orbital symmetry is occupied A1G. Don't worry about what that denotes. We have one occupied orbital. That's what's stated up there. And then here we have these natural orbital coefficients. That's what we're going to chat about here. And this is orbital 1, this is orbital 2, 3, 4, 5. And the coefficients for what they're comprised of are denoted by these numbers corresponding to the well-labeled constituents there. First number we're going to look at is the eigenvalue. The eigenvalue you can think of as the occupancy, essentially. So the first orbital has 2 electrons. And it's composed of a variety of S-type orbitals. That's what these coefficients here mean. And we can view that, and we will later, but it'll just look like this here. But in these simple cases, you can actually, I can, probably Tony can do it better than I can, but you can sort of start to visualize what these might look like even with these coefficients once you've done it a few different times. But this one's relatively trivial. We have a bunch of S orbitals that are contributing to this, so it's going to look S-like when we look at it. The second orbital here, 2, has an eigenvalue of 0, meaning there are no electrons in it. It's also composed mainly of S-type functions, so it'll look like another S orbital. In this case, we have negative and positive coefficients, so there should be a node in that one. And then orbitals 3, 4, and 5 have coefficients 1 in various p-style orbitals, px, py, and pz. So orbitals 3, 4, and 5 are p-like orbitals. And then 6 and 7 are some other diffuse s-like orbitals. Okay? So now let's go ahead and view some of those. I don't know, do you guys, I probably copied it too, but you guys might not have these cube files, but you can create them in the following way. I have, you probably don't have the scripts folder there. Do you have a scripts folder in your, is anyone in that folder?
It's not in this folder, but
okay. Yeah, so you can get it from your date 2 folder, or I can copy it in there, or you can copy it in directly. So actually, if you want to execute the following command, so if I copy from my day 2 folder the scripts directory, so copy -r means copy a directory. Now I want to copy that directory, and period denotes here, so I want to copy it there. So if you execute that command, you should now have a scripts directory. The first thing we want to do is create an fcheck file. And Tony's script for doing that is form.csh. So I'm going to call from the scripts directory this form.csh script. And I'm going to execute it on my helium atom job. And if I do that, I should generate this file. Okay? If you're not following along and you got lost and you don't have the scripts directory, I can give you these files later, or I can get you these. We can talk about how to generate them. Okay, but let's now generate these cube files. What is the cube one? AMO? Okay. So we want to create molecular orbitals, and we want to, from this set this job, and we want the first one. We should do something. It creates this file. Okay? Now I'm going to fly through that and do a few more of them. And I generated all of these cube files. Now what I'm going to do with them is I'm going to transfer them to my... So I have two tabs open, or three tabs actually, but this is my cluster tab. I'm logged into the cluster on this tab, and over here I'm on my local machine. Okay, so echo hostname, if you will just print out the name of the computer. Okay. I believe I already have these files here. So now we want to view these cube files. These are densities of essentially these orbitals that we want to look at. Okay. So orbital 1, orbital 2. So when we were talking about what they're composed of, I said these are S-like and these are P-like and so on. We want to view those and see if we were right. There are a variety of ways of viewing these files. I just sent a link to a program called Avogadro, which Tony mentioned on the second day. That has a Mac and PC versions. So you can download that and you can actually view the fcheck file directly in that case. So just transfer the fcheck file and you can look at all of the orbitals. Or you can use Tony's web interface. So I'm going to select this cube file. Takes a second to load. If it doesn't load, I'll do it locally.
It needs the an ISO value.
Yeah, how do I? Oh, cube options. That's gigantic.
0.02.
0.02?
0.02, yeah. For orbitals.
There we go. All that work to draw a sphere. So that's what it does look pretty S-like, at least to me. I don't know, you guys can debate that, I suppose. We're going to skip ahead to 3 because apparently this takes long. So remember, 1 and 2 I said were S-like. 2 had a node in it, so it could potentially be interesting. But let's skip ahead to 3 and see if it's anything different.
see that electron just moving around.
Yeah, just orbiting. Oh, this is also S light. When you do the AMO thing, does it print 2 orbitals per?
That's no, but it's ISO values. So there's the inner one and then the outer one, the positive and the negative.
No, I know, but this is AMO 3, which I would have P character in the.
Yeah. Not sure what's. Why don't you reload? No, the
This is a 2S.
reload the program.
This is a 2S orbital. Let me just see it. Let's go up to 4.
You know, up in the on your Chrome, just relaunch the page.
Well, I mean, it was different. Anyways, we can also do. We can double check it by. It's S light. That's 2S light. That's also something weird. So maybe it was right. There are P orbitals. So orbitals 4, 5, and 6 are all P light. Now, for some reason in the new version, this Avogadro in this operating system does not draw them default to drawing them different colors, but these one should be red and blue, or they should be plus and minus or whatever to denote that these lobes are different. You can annoy. It's an annoying thing to do. Okay, so that's a sort of generic P-looking orbital. Okay, so these are the unoccupied or virtual orbitals of our ground state helium atom solved in the Hartree-Fock level of theory. So now what we want to do is find other routes instead of comparing the orbital energies for the excited state. What we want to do is optimize the wave function in the first excited state. Okay? So in the hydrogen atom, you can actually just look at the orbital energies of your virtual orbitals, and you can get a reasonably good approximation for the hydrogen atom spectrum because there is no electron-electron interaction. In the helium atom or anything bigger, those unoccupied orbital energies will not be a good approximation of the excited state energies. Okay, so let's look at a way of computing this, and I should mention that we're going to Hartree-Fock, at least the non-time dependent version of it, cannot compute excited state energies unless you change the spin.
You can.
Single determinant?
Yes, if they're of different symmetry.
Right.
Which is kind of cheating.
Or a different spin, so I could compute the triplet.
Yes.
But for the sake of argument, let's just assume you can't for now. So we're going to look at the CAS-SCF method, which we're going to later use on molecules. In fact, this is basically a full CI for this simple case. But I have to emphasize that it is a different level of theory than Hartree-Fock, okay, which we used to compute our ground state energy and orbitals, and so on, that we were just looking at, that log file. So when you change level of theories, you need to also re-optimize the ground state. So I can't just go optimize the excited state in SCF level of theory, because it's a different level of theory, and I wouldn't be able to compare it to the Hartree-Fock ground state energy. Or at least generically you cannot. In this case it might be. Okay, so what I first am going to do then is to, again, optimize the ground state of helium, ground electronic state of helium. But now I'm going to, you'll see my input line for Gaussian changes a little bit because I want to change my level of theory. So I'm going to do CAS SCF. We'll talk about that in a second. And the rest of it is the same. Okay, the basis set I'm going to use is the same. I've changed my checkpoint file name. That's all fairly standard. So CAS SCF, you have to give it 2 numbers in parentheses after you call CAS SCF. CAS SCF stands for complete active space self-consistent field. So what we have to define is our active space. And essentially what this is the space of orbitals and electrons that I am allowing all possible excitations to happen in. What this is called, so this is called CAS SCF 2.5. 2, the first number in those parentheses, stands for the number of electrons that I'm allowing to move around. There are only 2 electrons in helium. They're starting in the same orbital, so I'm going to have 2. Okay. In the case of hydrogen, you would only have 1, for example. I will show examples of molecules later on today where we don't use all of the electrons, but just, for example, the valence electrons. Because in a lot of dye-like molecules, you have only valence to like pi-pi star transitions are the important transitions typically in large aromatic dyes. So you don't need to worry about 1s, 2s transitions to other orbitals. So we have these core valence separations, which is what CAS SCF was designed to take advantage of. So we don't have to think about excitations of core electrons into Rydberg orbitals or some crazy stuff. In the case of helium, this is essentially a full CI or close enough to it. So that first number is number of electrons. Second number is number of orbitals. So I have my 1s orbital, from which I'm getting my electrons. That must be included in that number. So we have 1 coming from the 1s, we have a 2s, and then we have 3 p's. So I'm going to stick with 5. So I have all of my n equals 1 and n equals 2 orbitals. In the case of helium, you're limited by how many. You could put 3 or 4 and mess around with it if you want, but this is what I chose. It doesn't really matter. In helium, it's a very simple case. Now, I've run this job, and you can look at the log file. This should be in your folders. And here again, I want to focus on the population analysis. And if we look initially, ignoring the eigenvalue, but we look at the values that are composing, from the components here, are composing orbitals 1, 2, 3, 4, and 5, we see that it's quite similar to what we were seeing, at least qualitatively, similar to what we were seeing from the Hartree-Fock description, in that orbital 1 has all positive values only in the s-type orbitals. Orbital 2 has only s-type contribution, but there is one negative. Orbital 3 is basically only p-type. Orbital 4 is also only p-type. Now orbital 5 actually is s-type. So that's a little bit different, actually. But essentially the same. The difference here is that we don't have exactly 2 in the first orbital, but rather 1.98 as our eigenvalue for orbital 1, and then 0.700771 for orbitals 2, and some other small numbers are 3 and 4. So CAS-SCF is a multi-determinant method, so allowing for these partial occupancies of these different orbitals, non-integer occupancies. But essentially, I mean, this contribution is very, very small. So this is essentially a very similar result to what we were getting from the Hartree-Fock ground state. The important, unimportant number here is denoted at the bottom, this HF equals negative 2.885314. Even though that says HF equals, that is the CAS-SCF energy for the helium atom in its ground state. So this is going to be an important number for us to keep track of when we want to compute, for example, vertical excitation energies. Because this will be our ground state energy, and then we'll get a first excited state energy and a second excited state, and so on. And then we get vertical excitations by subtracting the excited state energy from the ground state energy.
The units of that are Hartrees?
Hartrees, yes. That's in Hartrees. So Hartrees to convert to kcals per mole is 627 times 627.5095. Or you can Google it. And the electron volts is like times 27. 27 point something. But you can Google it. Okay, so we re-optimized the ground state wave function for helium in the CAS-SCF 2.5 level of theory. Now we want to optimize the first excited state, or what we might think is the first excited state. State 2. Okay, so now we look at the input file for state 2. Tony, is it state 0 or state 1 is the first? Do they default to 1 is the first one? So n root equals 1 is the first one, right? You don't remember?
They are not consistent within.
Okay. I was assuming it was n root equals 1. But now I'm questioning myself, of course. Okay, so assuming that we're starting at 1, what we have here is essentially the same exact thing as we had before, except for n root equals 2. Assuming that
you n root one is ground state,
yeah,
because you could actually want that. Whereas in TBD at T, you don't want root equals 1.
Yeah.
Because that's the ground state. And so, yeah.
So the only difference is that n root equals 2. The default is, as I think we've just decided, n root equals 1, which is the ground state. So in the previous file where I did not have this n root equals 2, it defaulted to setting n root equal to 1. I would have had the equivalent input file, or the equivalent output file, had I put in there n root equal to 1, requesting the first root of this multi-determinant method. Now I want to request the second root, okay, which is the first excited state. With the caveat that I have what spin state here? Singlet. So I denote my spin state. So this is going to be the second root of the singlet of determinants that are of the singlet spin state.
The word hydrogen atom in there, is that?
Oh, that was just because I copied it from something else.
Okay, I just was making
Title
sure.
card.
This could be Bodie McBoatface, you know.
Yeah, okay. I just was making sure that
Board
that
face.
wasn't designed to tell us something.
It's completely. It's only for the sake of the person using it to keep track of things. Okay. So let's look at the log file now. and I like to look at the occupations. Again, now this is the second root, multi-determinant, singlet spin state, helium atom. So our first singlet excited state, and it is coming from contributions of, so we have a partially occupied s orbital and another partially occupied s orbital. Okay?
Does it give us the configurations a little more?
What do you mean?
I mean, it's like what the excitation is.
I don't think so.
That's yeah.
You know, because they don't compute the oscillators, right?
Oh.
So they don't actually compute the ground state wave function. They don't look at the root equals 1.
Well, they got to calculate it.
Yeah, but
Because first, that excited state has to be orthogonal to it. And so, which is a pain,
but then they don't actually compute, for example, the whatever transition dipole moment projection into or
so,
from 1 to the
up
other.
just a little bit further.
Up?
Up. Yeah, okay. So that's the density matrix, up a little bit higher. But yeah.
Oh, eigenvalue 1 here.
Yeah, so those are the CI coefficients for the contributions of the various orbitals to, so the ground state, and then the ground state is, well, and actually a little bit higher still. Above, yeah, because I think it gives us the list of configurations.
Where? Here?
Oh,
Yeah, above that. Okay, there you go. So that's the configuration 1, 2 electrons in orbital 1, configuration 2, alpha, beta.
Oh, I see.
And then, you know,
I see.
and then.
So he's looking at this.
I mean, it's like, you know, only if you're sort of going nuts do you really care about that. But
Yeah.
some of us sort of cherish those.
Yeah, but you can get that. You're getting that same information. Well, you don't see the ground state. This is excited state. So you see where the occupations are here. But okay, sure, fine. All right, so you can do the same thing for 3 if you want, and so you just change n root equals to 3. I'm also, by the way, changing my checkpoint file each time. That's so I could view the orbitals optimized in that root if I wanted to. But we already know that triplets are going to be important here, so let's talk about how to do that. So we're going to look at this triplet.state1.gin file. And so everything looks pretty similar. This looks like exactly like the ground state CAS-SCF calculation, except that I've changed my spin state from a singlet to a triplet. This is the first root of the triplet. You can't have a triplet in the 1s doubly occupied configuration. So your first triplet state will be an excited state of helium. There's no way you can make a triplet in the single orbital. Okay, so the only way to make a triplet is to put one of them up into a higher energy orbital. So we can look at the log file for that, and you can look at whatever part you want. I like to look at this part. Okay, here we have actually integers here, which is nice. But we have the 1s, 2s configuration, and probably it would be AA this time instead of AB. Oh no, wait, this is AA, sorry. This is the first triplet state, so it's AA. It doesn't have the configuration for the singlet because it's a triplet. So it's AA, 1s, 2s. Okay, so that's the kind of thing you look at. What is also important here then is to compare the energy of the triplet. So here's this Hartree-Fock energy, negative 2.1452613, which is some number I'm never going to remember. So you could copy that to Excel spreadsheet or whatever, but right now I just want to compare to the energy of the first excited singlet state, which is my CAS-SCF state 2. And I want to find the Hartree-Fock energy. Okay, so the singlet excitation energy is negative 2.0865, okay? And the triplet first excited state energy is negative 2.14. So which of those is lower? Triplet. Okay, good. So, as Lauren pointed out, we expected that. Okay, okay, so good. That's how to do CAS-SCF calculations, multi-determinant calculations on relatively simple helium atom system. You are welcome to play around with Avogadro and view the different checkpoint files, create F-checks from your checkpoint files. So Avogadro will only view F-check files, not checkpoint files. But we're going to move on to molecules so that we can do systems that are more inherently interesting. Let's see. I want to go back to this, or let's just go on. So multi-determinant wave functions. Let's get this. Molecular orbital theory, should we do this? Instead, let's just look at ethylene. So the molecule we're going to first look at is ethylene. Okay, this is C2H4. And this is going to motivate using an active space that is not just all electrons in our system. And we're going to do CAS-SCF calculations to attempt to compute the excited state energies. Okay, so having skipped over molecular orbital theory, these are the occupied molecular orbitals, or the molecular orbital diagram of ethylene is depicted on the right of this slide. And what this denotes is we have a bunch of occupied sigma orbitals, sigma denoting sigma bond, right? So, and then we have a single pi orbital that is doubly occupied, and then above that we have pi star and sigma star orbitals. Is anyone confused about that, or how to generate a molecular orbital diagram, or do you want to look at it later and then come ask me? Okay, but this is also trying to depict the relative energies of these types of orbitals. The sigma orbitals are much lower in energy than the pi orbitals. So what would we expect the first excitation, single excitation that is, of ethylene to be, given this energy diagram?
Pi star transition.
Good. So we would anticipate, because this energy difference is much smaller than that energy difference, it's most likely we will see it will be lower energy to see a pi star transition. Okay, so that's what's denoted here. We're going to see a pi star transition. So this motivates this CAS-SCF method, where instead of allowing excitations of all of those sigma, so we essentially what CASSCF does is optimize this multi-determinant thing, which I know I skipped over that. But it comes from moving, potentially allowing all electrons to occupy all possible orbitals in my basis. So if this were sort of my basis, I would allow, and this is going to denote my active space, but if I were allowed to all electrons to occupy all orbitals, in the case of ethylene, that would mean I would also allow any sigma orbital to occupy the pi star, to occupy the sigma star, and then if I had any other orbitals also occupying those. That's great. If you could do that, you can solve the full CI wave function, and that's fantastic, but it's extremely computationally demanding. So we want to avoid that if we can and if it makes sense for our system. What complete active space self-consistent field does is isolate electrons and orbitals in which you allow all excitations, but you only allow them in that space. So in this picture, I am isolating 6 electrons in 6 orbitals. Okay? And I'm saying I will create all possible determinants which have any possible excitations within this space. You could do the combinatorics to figure out how that is. In the case of ethylene, we're going to just do 2 electrons in 2 orbitals. Because we want that pi star to be our active space. So you can think about then just looking like this. Okay, and so you have 2 electrons in 2 orbitals. Oh, and these pictures on the right are denoting some of the excitations you might allow in that space.
Do you always have to have the same number of electrons in
No.
the Should you?
No, not necessarily. So it depends on the system. I mean, you saw in helium I had 2 electrons and 5 orbitals. That was somewhat arbitrary as well. That did have my.
The art.
It is a bit of the art. So in the case of pi systems, it's often the case just because you have the pi, I mean, just follow it, it should be the same. But it just depends. What you want to think about in determining your active space is what are the likely energy gaps between the occupied orbitals and then the unoccupied orbitals as well. So if there's inherent energy gaps like there are in pi systems between the pi orbitals and the sigma orbitals, then it makes sense to select only the pi orbitals. But it depends what type of excitations in the system and all this other stuff. What is important is that when you select a doubly occupied orbital, so let's say I was making this my active space, right? I have 2 electrons and 4 orbitals. So make sure you count both the electrons in that orbital and that orbital in the space. Okay? If I wanted to go from this active space, which is 2 electrons and 4 orbitals, and I wanted to include this orbital, I must include also its electrons. Right? So if I went down to that, it would be 4 electrons and 5 orbitals. Okay, well, this is just denoting here how we create our pi and pi star. For ethylene, we create our pi and pi star transitions. So a pi orbital here is where you have the plus plus and the minus minus of the individual p orbitals coming together to create a bonding orbital. And then if you have a node in between them, that's the anti-bonding orbital. That's going to be important. We'll look at the orbitals of ethylene, but in particular we move on to benzene, and then today for your project you're going to do anthracene. If you want, you can also do the benzene dimer. It can, if you aren't comfortable with sort of picking out what pi orbitals are, it will be a challenge, although this will be experience in attempting to do that. Okay, so I guess I'm going to do a CAS calculation. Oh, I think what I wanted to do here was just view the orbitals, and then we're going to do the CAS calculation for benzene. So let's just get experience viewing the orbitals. I'm going to just use Gauss view locally because the other things are slow. But you can do this using Avogadro, or if you have a Mac, we can give you Gauss view. actually, Bradley and Rachel, there may be Gaussian on this IMAX. There should be already on there, and we'll just figure out how to use it. So I can Gauss view this checkpoint file directly. One thing I should mention here is that the workflow for doing remember we want to have the molecule in its ground state geometry. In the case of the helium atom, we don't have to do any geometry optimization. It's a single atom. We just need to optimize the wave function. In the case of a molecule where we have also nuclear degrees of freedom that we need to optimize, you need to first optimize the geometry. Typically, a CAS calculation, you don't optimize the geometry in the CAS level of theory. You typically do it in a DFT level of theory like B3-lib. Use some basis set. And try to be consistent at least with the basis sets. But probably doesn't matter too much. But here, the job that I'm viewing the checkpoint file of for this is a geometry optimization in the B3-lib density functional theory level of theory. And I want to view the orbitals just so we have some experience looking at the orbitals, and then we can see that our molecular orbital diagrams actually are a useful tool. So let me just select a few of these. So in Gauss view, when I load the checkpoint file, it gives me these are my orbitals, my first orbital, the lowest energy orbitals, and so on. They try to depict the occupancy with those arrows up and down. I wouldn't always believe them, but it draws this green line between the HOMO, highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. So if I select here on the right, if I pick these little squares, it'll draw the different orbitals. This is my highest occupied molecular orbital. Okay, and this is representative of a pi bonding orbit. You can think of this again as coming from the p orbitals of the carbon. These two carbons coming together with the same plus or minus, alpha, whatever you want to call it, lobes coming together and forming your pi orbital. Conversely, this is the pi star orbital. So again, these look like essentially p orbitals with my carbon atoms, and they're coming together, but in the wrong orientation to form a bond, and they have a node in between them, and thus are repulsive, or my pi star antibonding. So this is orbital 4. This is a carbon-hydrogen sigma orbital, for example. This is another carbon-hydrogen sigma orbital. This is some other combination of carbon-carbon and carbon-hydrogen or something. So this is important. The difference between this orbital and this orbital. Does anyone see? They look pretty similar, right? Good. Good, perfect. So you notice here, I don't see the hydrogens. These little lobes right here are covering my hydrogens. Whereas this one, I can see the hydrogen. Oh, no, sorry. This one, they're not covering the hydrogens. It's in a different plane, right? So the first one that I was showing is what? What kind of orbital is that? No, it's a sigma. It's the carbon-hydrogen sigma orbital, but it's the most anti-symmetric sigma orbital of the carbon hydrogens, of the bonding orbitals. That has the most nodes in it. But notice it's just so the carbons and hydrogens the carbon-hydrogen bond is covered up by density here, right? As opposed to this one. You can also actually, maybe can't see the numbers here, but you can see these energies. Yeah, blurry here, but these are the energies of the orbitals, and if we're going to do a complete active, the CAS-SCF calculation where we just have two, where we're using the pi star, it's better if the energy separations of these orbitals is large. But instead of doing ethylene case, we'll move on to benzene because it's more applicable to the rest to your project. And then we'll actually look at the orbitals again, get more practice in that, and then we'll do CAS calculations.
And can you do the same type of visualization as well in Avogadro?
Yes. Maybe a bit clunkier. I would do it in Avogadro, except that for some reason in Avogadro in this OS, it doesn't automatically change the colors of the lobes. It makes them all black, which is just annoying, and then I have to go change it. So I don't want to do that. But you should be able to, and if you can't, we can chat. Okay, so now I want to do benzene, and I want to compute the excited state energies for let's say the first 3 excited states of benzene. So what I'm going to do, the workflow I'm going to follow is I'm going to do a geometry optimization of benzene in the B3 lip level of theory. I'm going to view my orbitals, because as we'll see, some will be kind of out of order for the to select my pi star active space for my CAS calculations. Okay, so we'll start by performing a geometry optimization in the B3 lip level of theory. So I did that here. We should have had some more basis functions. And it generates, I ran it already, and you already have these files as well, so it generated a log file. We can view that if you want to. As we add more and more atoms and electrons and orbitals, obviously they're going to be, the population analyses are going to be harder to view. It's not as simple as helium, so we're not going to spend too much time doing that in the log file. Instead, we're going to use Gauss view to visualize the orbitals. So I'm going to select a few of these. I should remember which ones. So how many pi orbitals are there in benzene? Good. 3 pi star. How did you get that?
There's 3 double bonds.
Huh?
There's 3 double bonds. You know, if I draw it.
Okay, so the molecular orbital way of thinking about it would be you have 6 carbons contributing 6 pi orbitals, which should create 6 different molecular orbitals.
Right.
And if you know that you also have 6 electrons in there, and the molecular orbitals are doubly occupied, you're going to have 3 that have 2 electrons each, and then 3 that don't have any electrons. So you have 3 bonding and 3 anti-bonding.
So why is that green line not between where it's gone?
It's because it's silly.
Oh, okay.
It's because the reason that green line is actually the 0 of energy, whatever they've denoted. So all the orbitals below that have a negative energy that apparently in this calculation.
It's Fermi level.
Fermi level.
For a molecule.
And this is why, So let's start with the, okay, so let's start with the highest occupied molecular orbital here. Okay, this is a pi orbital. The HOMO -1, another pi orbital.
Are those the same energy?
Pretty much. Okay, now HOMO minus 2 is this orbital. Okay, is this a pi orbital? No, why not? How do you know?
It's in the plane of the molecule and not above and below.
So notice that the pi orbitals, right, they each have nodes in the plane of the benzene. So any pi orbital, because it's being composed of these p orbitals, which all have planes in the plane of the benzene, the molecular orbitals must maintain that. So we can clearly see that this does not have a node in the plane of the benzene. Okay, so if we told Gaussian we want to do Cas SCF 6 in this case, 6 electrons, 6 orbitals, what it defaults to doing is selecting the HOMO minus 1, HOMO minus 2 in that case to get 6 electrons, and then LUMO plus 1, LUMO plus 2 to fill out the 6 orbitals. Is that reasonably clear? In this case, that would do the wrong thing. It would not be, wrong in the sense if we want our active space to be pi star, it would not be a full pi star active space. So I'm telling you it's the wrong thing. So we have to go find the other fully symmetric pi orbital. So the lowest pi orbital would be the fully symmetric one. So what was that going to look like? Going to look like a hamburger. A hamburger.
I guess you just, no, it's
Or a veggie burger if you're vegetarian. It's organic.
no, you wouldn't want to eat benzene.
Disclaimer, no benzenes were hurt during the calculation of this wave function. Okay, so here in orbital 17, we have our fully symmetric pi bonding orbital. And orbital 19 is the HOMO minus 2 that we would like to put it on. So I'm not going to keep notes on this now because I've already done the calculation. But when you're doing anthracene, you're going to note down what I would recommend doing is starting with a list of, you don't have to start at 1, but start writing out what is the character of each orbital starting at HOMO minus 10 or something like that. Okay? It's good practice anyways, just to try to start characterizing some of these things. But some of it can be complicated, but I hope that, anthracene should be very similar, right? Pi orbitals will have nodes in the plane of the anthracene molecule, so you should be able to pick those out. Okay, so now let's look at the LUMOs, the unoccupied, the unoccupied orbitals. Okay, so LUMO looks like this. Okay. Again, we have a node in the plane of the benzene, and we have other multiple nodes in the perpendicular planes. LUMO plus 1, again, another pi star orbital. Node in the plane of the benzene. Okay, this is LUMO plus 2. Is this a pi star orbital? No. It's some funky other way. It's a CH sigma star orbital. Fully symmetric though, so it lowers the energy, I guess. Very symmetric. Okay, so this is LUMO plus 3. Is this a pi star orbital? No. Okay, this is LUMO plus 4. Is this a pi star orbital? No. Okay, LUMO plus something else. Is this a pi star orbital? Nope. Okay, LUMO plus some other thing. Is this a pi star orbital? No. Nope. There he is. Okay, so this one's way high up there. Why is it way high in energy? Yeah, it's got a bunch of nodes in there, right? So you'll see, I think in anthracene there's typically there's at least 2 that are out of the that you'll have to find that are not in automatically in the LUMO, in the unoccupied active space. But certainly the fully antisymmetric anthracene one will be way high in energy. Okay, so if I were doing the project, I would have noted down some character of each of those orbitals, and when I finally find this one, I would say, okay, great, this is the pi star orbital, and I've denoted its number. The number is going to be important, okay? And I want also the numbers of the, in this case, LUMO, LUMO plus 1, and LUMO plus 2, because those will be the 3 unoccupied orbitals in my 6-6 active space. Okay, so, but we did that, we looked at those orbitals, we optimized the geometry. Okay, now let's do a CAS-SEF calculation. Okay. We haven't done reading wave functions.
Yeah,
Okay. So that checkpoint file that was generated from that B3-lip optimization that I just viewed in Gaussian, that essentially contains my B3-lip optimized wave function. I'm going to want to read that in from as my initial guess for my CAS-SEF calculation. The way that I do that is by, in my percent check line, it is a input-output line. So if I put that percent check and there's no file that is called, it will just create that file and write its new wave function to it. But if a file that is named that already exists, I can read, guess equals read, the wave function from that input file. So how do I do that? Well, before I would run this job, I would copy my B3-lip opt checkpoint file to a file named that. So then I make a copy of that wave function using Linux commands or whatever you want. And then I'm going to read it in this job. I'm going to read it in, but I'm also going to alter it. What I'm going to alter is I'm going to switch orbitals 17 and 19 and orbitals 24 and 30. Those were my, so 17 was my fully symmetric pi orbital, and 19 is HOMO minus 2, which was some sort of sigma orbital, and then 24 is LUMO plus 2, and 30 was that pi star orbital that was way high in energy.
So you're just doing that to get that within your 6 orbital range? You're
right.
Just basically moving down.
Yeah, all I'm saying is, hey, I want to get that wave. I want to make my LUMO plus 2 that sigma star orbital, and I want to make my HOMO minus 2 that pi orbital. Up until this link 1, that's all that part of the code does. That job, it'll run a Gaussian job. That all it does is swap those pairs of orbitals and essentially print a new wave function that's not re-optimized at all. It just swaps those things. Okay? What I have here is a slightly more complicated input file. So instead of running that and then generating this new checkpoint file and then running another Gaussian job with a new input file, which reads that in and then performs the CAS-SEF optimization, you can link two Gaussian jobs in the same input file. Because this job is simply swapping orbitals, it's not going to be time consuming. I don't really care about visualizing its output so much as reading it in and doing a ground state. Oh, I should also mention, so I had the guess equals read, comma alter. Guess equals read, comma alter, what that does, it reads in the wave function from that checkpoint file, and then it tells Gaussian that what I want to do is move things around. I'm going to perform an alteration. And then geom equals check, short for read the geometry from the checkpoint file as well. Okay? So I'm going to, from that file, which I've copied from my D3 lib optimized wave function checkpoint file, it has both geometry, the nuclear geometry, and then the optimized wave function for that geometry. That's why I don't have to give it a geometry here. It's reading it from the checkpoint file. Okay, then after link 1 is a new job, where, again, I read the same checkpoint file, but now that's been altered. And I want to perform CASSF root 1, guess equals read, pop equals method, geom equals check. So basically everything else is the same, but I'm going to, actually this, because I don't have that alter line, I should be doing, I am doing a wave function optimization for this geometry at this level of theory. And again, I don't have a geometry here. I just have a 0, 1. There's a common set of space. It doesn't matter. You can put space there if you want. Geometry is coming from the checkpoint file.
So pop equals or pop
Natural.
parentheses does the same thing for natural?
Yeah. So we run this job, and and I look at the log file. In this case, there should actually be basically 2 Gaussian outputs, because there's a link 1 in the middle of that thing, so it's going to run 2 jobs. So if I search for the string entering Gaussian, let me show it twice. Tony, does the first one do a wave function optimization?
Yeah,
Oh, it does. So I don't actually need to do the second one.
yeah.
So the alter, so I could just get rid of that bottom thing. But it doesn't matter. I guess it just does the same thing.
If you have it only in there,
In the alter?
yeah,
Okay.
then it would
But
do it and stop. Which, sending something off somewhere else that, if you want to check, make sure that it's going to work.
yeah. Okay, but so I have 2 jobs that are essentially doing the same thing. But that's fine. Okay, so to keep moving forward, all I care about here, to some extent, is this energy, which is at the very bottom of my file, and then I go search for Hartree-Fock equals. This is my energy. This is the CASSF 66 ground state energy for benzene. Okay. You want to keep track of that, and in this case I did actually. I started a file where I'm going to keep track of my energies. So I copied and pasted that energy into there. I'm denoting that singlet because it was spin, and delta E is going to be relative to the ground state, so this is 0. I'm setting the ground state energy to 0. Okay, we haven't looked at the other ones. Okay, so apparently I can just get rid of this bottom thing. Oh, but this is, actually I can't, because here I do a ground state optimization, and here I do an nRT2 optimization.
But if you read in, if you read in your root 1.
Yeah, it would do this. It would do the same thing. Yeah. Okay, so what I'm doing in the first thing is the exact same thing as I was doing for the ground state CASSF. I'm reading in my D3 lib geometry and wave function. I'm doing a swap. In this case, as it turns out, I'm also doing then the CASSF ground state optimization. That gets printed into this checkpoint file, which I read in now. Again, geometry and the wave function. But now I want the n root equals 2, the root 2, or the energy, or I want to optimize the first excited state. first singlet excited state for benzene within the CASA-CF66 approximation. Okay, I can look at that log file. So I'm looking at the log file here. And we can see the energy is this. And I would put it in this file here. Actually, it's there. So I'd start populating this file, and then we can reorder it later. I've obviously already reordered it. Okay, and then if we want to do the triplet, let's look at the triplet. This first job is identical, except that I have a triplet here. I still swap. So every time I start one of these jobs, notice my checkpoint file is named differently. So for every one of these, I've initially copied the B3lib checkpoint file to that. So I've made multiple copies of that B3lib checkpoint file. Yeah, you make a bunch of copies of it, and then you perform these different operations on it.
A sort of a wonderful thing they did in Gaussian 09E was they added the command old check. And so if you put old check there, it reads the old one in, so you don't have to do that copy.
And there's a new check as well?
Just check.
Okay. Well, we're not using that, so you have to make individual copies of that optimized wave function in geometry. Okay, and then here, well, essentially I'm doing the same thing as I was doing above, but I've now put my n root equals 1, which was defaulted to there anyway, and I'm in my triplet state. Okay, and I can look at the energy of that, and we can grab it from here, copy and paste it into your data file, or put it in an Excel spreadsheet, or whatever you want to do. Okay, so then you start to accumulate these, maintain whether they're singlet and triplet in what state, and so on and so forth, and then you can compute their energies relative to the ground state. In this case, these energies are in Hartree, these negative 230s and such, but then I've taken the difference between state 2 and state 1 and multiplied it by whatever unit conversion to get to electron volts over there on the right. You should also be able to view, I don't remember how this works. Let's see. The nature of the excited state. That's another thing we wanted to do, right? Check. So we look at the orbitals that get occupied, and let's see what Gaussian does. Good. Actually, that's something halfway useful. Okay, so now let's look at some of these orbitals that are occupied. They don't, for some reason, doesn't put the energies in this. But it is attempting to denote the occupancy here. That says that 21 is singly occupied and 22 is singly occupied. So that's good. So 16 is some sigma orbital, orbital. Okay. 19 is our hamburger. 20 is another pi orbital. They're both doubly occupied. And 21 is a pi orbital, singly occupied. And then 22 is a singly occupied pi star orbital. So this is the first triplet state of benzene, and what we, in the CAS-SCF66 approximation anyways. And what we've seen is that all you do is excite one electron from a pi orbital to a pi star orbital, which is essentially dictated by our input wave function and our choice of active space. But what's important to note is that it is taking the highest energy pi orbital and the lowest energy pi star orbital and doing that transition within them. And let's see, is that, yeah, okay. So remember our active space is 6, 6, so we have to look at 19. Is our pi orbital 20? Is our pi orbital, those are in our active space. This is another pi orbital in our active space, pi star, pi star. Pi star, all still in our active space, so that's all good. And we don't see the transition, the first transition, so from the singlet state where you have three doubly occupied pi orbitals to the first triplet state where you have a singly occupied pi and a singly occupied pi star. That transition is not between the highest energy pi star orbital and a pi orbital. Okay. This being the highest energy pi star orbital, it doesn't have any electrons in it in this state. Okay. Any questions on that? Okay, so that's the type of thing you can do. Again, you can use Avogadro to do that same sort of visual analysis of the visualization of the orbitals if you create an FCheck file. Avogadro will not read the binary checkpoint file. You have to create the formatted checkpoint file. To do so, you run that form.csh script that Tony provided for you on Tuesday. Okay? Do you want me to show you how to do that? I'll know how to do that. So if I wanted to view that checkpoint file with Avogadro, I would just generate run form.csh on benzene CAS-SCF66 triplet en route 1. The other way is to view the other way, if you don't have Gauss view, to visualize the molecular orbitals is to create cube files using that aonmodel.chs script that Tony provided, and you just have to generate. You have to know the number of the molecular orbital that you want to generate. That is, in my opinion, fairly cumbersome. So I would figure out another way. One thing I want to mention, since we did mention a little bit about spectroscopy, at least for whatever reason, Gaussian does not. So what we were getting here is energies. Energy differences, hopefully, vertical excitation energies if you want, between the ground and excited states. If you want to compare to spectroscopy, you need an additional, you don't just need the energy, but you need also what? Does anyone know? So think about what a spectrum looks like. You have peaks at different energies, right? Pardon me? So energy and wavelength you can convert between, okay? You need intensity, right? For spectroscopy, you say you have a peak at a certain energy. That peak has a certain height, which is intensity or whatever it is in spectroscopy. We don't have that. We just say, here, we just have an energy difference. We say that there is a state at this energy difference. What we don't have is called the oscillator strength of that transition. Right? So what you would have to do from quantum mechanics is compute the transition dipole moment operator between the ground state and the excited state wave function. So you'd make that rocket thing and solve for that. Now, I'm not exactly sure, considering that they have those roots, why they don't do that, or at least print it out in this program, but it can be done with those two wave functions. It's just not automatically printed out when you perform CAS-SCF calculations here.
Yeah, I think you would want to have the wave function optimized for the ground state.
Yeah.
And then the wave function optimized for the excited state.
Yeah.
Those are going to be two separate checkpoint files.
So you'd have to write your own little script to read those 2 checkpoint files and then perform that operator integration.
Whereas with the TDDFT,
Right.
you didn't alter the ground state, and
Right.
so you have all the information.
So to put this in a little bit broader perspective of the field of sort of doing computational spectroscopy, as it were, the CAS-SCF method, while it is relatively informative to describe characters of excited states, because you have to actually think about orbitals and those kinds of things, so it's a good pedagogical tool in that sense. It's actually not what is typically used if you were going to compute excited states for an organic dye, for example. In particular, if it has a lot of excited states. Obviously, doing all of these calculations for 1, 2, or 3 is already becoming cumbersome. But for a large, messy molecule, you might have tens to hundreds of excited states that become important for a UV-Vis spectra, for example. So you don't want to do that with this. And not only that, you don't get the oscillator strengths, at least easily, out of this. So the other technique, which we won't talk more about really, but is something you should be aware of, is the time-dependent formalism. And while maybe the formalism is harder, the theory might be slightly harder, arguably, potentially. Actually, the input for Gaussian and the computation of those excited states is actually a lot easier. In one single file, you can just say, do TDDFT, I want 30 states. I don't define an active space. I don't do any of that. And I just get out, assuming it converges, I get out the energies and oscillator strengths for all of those excitations. So, given that, you might ask, why do we even do this? The reason is it's a pedagogical tool. It's to learn to characterize and think about what orbitals look like and what those states actually look like, rather than just getting numbers and oscillator strengths out. Okay, that's it for today. Any questions? The project is posted both at on the last slide of the presentation, which I'll put up here, but also in the syllabus that I sent out. But no, naphthalene, not anthracene. But you can do
I was wondering when you jumped ahead to anthracene.
Well, last year I had them do naphthalene and anthracene, but anthracene can be a bit cumbersome. So I probably shouldn't have given you what active space you should use, but that's what it's 1010. But I want you to compute the first 3 excited states, energies of the first 3 excited states of naphthalene. The procedure that you should follow is to perform a geometry optimization first. Then remember, make sure that the geometry optimization converges. Then you're going to want to copy that optimized checkpoint file to multiple different inputs and perform your CAS-SCF calculation. But you're going to have to do some switching of the orbitals. Okay, so you're going to take that checkpoint file, view the orbitals, write the nature of each of the orbitals out on a notebook or whatever, and then decide which ones you have to switch in order to perform your CAS-SCF 1010 or pi star active space. Switch. Okay. Any questions? All right, great.